So these are counters, and a counter is a device that goes through a sequence of numbers. When you're talking about n number system, and you go through those states, or you go through the simples, we actually call that a counter. So it's usually developed using flip-flops. All those flip-flops we have discussed about can actually be used to develop these counters. And you can be able to see, like now, an example is when you're counting from 0, 1, 2, 3, then you start repeating. So you go in a circular manner. You move from 0, you go to 1, from 1 you go to 2, from 2 you go to 3. Then you go back to 0. That's a counter. They usually have a clock, and there are two types, which are basically synchronous and asynchronous. And I've just discussed about those two types of devices. So those descriptions are still the same, they don't change. Then let's look at the design of synchronous counters. The steps for designing: number one, determine the number of states that you will go through. So these are states, not steps. So determine the states. The number of states, like what we have up here. How many states are these? How many states are those? Amina, how many states are you seeing there? So you guys, I hope you are getting me.
Six steps.
States.
4.
There are 4. 0, 1, 2, 3. These are 4 states. These are actually 4 states. So determine the number of flip-flops you're going to use, of course, from the number of states. And you're going to use this formula 2 to the power n small is equals to n capital, where n capital is the number of states. N is the number of flip-flops. So if I have 4 states here, then you expect us to have 2 flip-flops, because 2 to the power 2 is equals to n. You can use this formula to be able to determine that. Of course, if you are dealing with a number of states which are not powers of 2, then you're going to use this formula and you round it off to a higher number always. So then use the transition diagrams to obtain the inputs that we have to the flip-flops. Of course, you will have developed a truth table for the same. From that truth table, you are expected to get Boolean expressions, and from the Boolean expressions, then you are expected to get the diagram. So I think I will be able to do a simple design. I will not go to this design which is down there. I'll just do a very simple one of counting 0, 1, 2, 3. So let's do it together. Actually, that's all about this. We are just now designing. That's all about the counters you expected. So I just want to design one, then you can see what next. So the question will be design a counter. So we design a counter to go through 0, 1, 2, 3. Then starts from 0 again and continues the same sequence. So the first thing we are being told, we determine the number of states. How many states are there? Capital N, number of states. So 4 states. Number of flip-flops, small n, is equals to 2 flip-flops. And please note that I'm using the formula. So from here, now we do the truth table. So we have 2 flip-flops. We do the truth table here for the 2 flip-flops. So we have A, so I want you to look at this keenly. Then we have B. We can call this present state. We just call it PS. And then the next one, we call it next states. And then the next one, we call it flip-flop inputs. So next state still will be AB. And flip-flop inputs, we're just going to call them DA and DB, because our flip-flops will be given by the 2 of them. So those 2 of them, we just call them, the inputs, we call them DA and DB, because we say one flip-flop has got 1 input. And therefore, if you put 0 present state, please tell me what's the next state when you are at 0, 0? Now we are representing them in binary. So if you are at 0, 0, or if you are at 0, what's your next state?
0, 1.
It will be 0, 1 because it's 1 decimal, and therefore it is actually 0, 1. So you indicate here 0, 1. Let's move down first of all. We do the present state and next state. If I'm at 0, 1, what's my next state?
1, 0.
It's 1, 0, that's correct. If I'm at 1, 0, what's my next state?
1, 1.
So if we are at 1, 0, my next state will be 1, 1. If I'm at 1, 1, what's my next state?
0, 1, 1. No, 0, 0.
You go back to 0. So we have 0, 0. Now, this is your present state, next state, which means if you are here, you move to 1. If you are here, you move to 2. If you are here, this is your present state, you move to your next state, which is 3. If you are here, you move to this one. That's what it means. And you change them to binary, they are represented this way. So let's look at the DA and DB now. And what enables us to get that? Please look at A present state, A next state. If you look at the D flip-flop, we said if we are moving from 0 to 0, what should be D?
0.
It should be 0. We had a table down there. It should be 0. Then what is DB? Sorry. What's DB for B? 0 to 1.
1.
It should be 1. That's correct also. Now let's look at the next one. This is 0A, 1A. So 1 present state, 0, 1, 0 present state, 1 next state. What should be DA?
One.
Should be 1 because 0 to 1 is 1. Anyway, let me do for D all of them, first of all. So 1 to 1 for D?
One.
Should be 1, that's correct. 1 to 0, what is D?
0.
That's correct. So let's do for B now. B will be 1 to 0.
Which is 0.
1 to 0.
0.
Is 0. Then the next one is B. B present state is here 0. B next state is here 1. So 0 to 1.
One.
By the way, it's very easy to note this. You don't even need to look at the present state. Look at the next state. Our next state will always be the one we are transferring to the output. Like for A, our next state was 0, 1, 1, 0. That's what you have here. Our next state for B is 1, 0, 1, 0. That's what we have here. So 1, then 0. Please note that that's how it's simple, how simple it is. Just transfer what you have at the output, have it in D. So what you have at the output, transfer it here. The next step is to do Boolean expressions for DA and DB. How do you do that? Look at DA. We have a 1 here, another 1 here. Go to the input. What's A?
0.
0. If it's 0, what do you do with A? You invert it, eh?
Yes.
What's B?
1.
1. So what do you do?
It's B, just B.
We don't invert it. Then look at the next one for DA. Move to the input, 1, 0. What does that mean?
There will be A, B bar.
A, B bar. Effectively, what is this? What's A bar B or A, B bar?
A, B. A plus B.
AX
A plus B. Or.
It's AX or B. Please remember X or is represented using this symbol here. Now what about DB? Get me the expression for DB based on what you have done here.
AB bar.
It will be A.
So before you
B
move on,
bar. Yes.
B bar.
yeah, I just want to understand how you got the expression for DA. Gotta be lost.
For DA, look at the ones. This one here and this one. Go to the inputs. Pick this one and pick this one. But you don't pick 0, 1. You pick the A, B. So if A is 0, invert it. So pick for the next one is A is 1, B is 0. So you invert B. That's why we have A bar B or A B bar. Is it okay?
Okay. Yeah.
So now when you're looking at this one here and this one. So the first one, go to the input. What do you have here?
A by B bar.
It's A bar B bar. That's correct. A bar B bar. Or the next one is this one. Pick these ones.
A, B bar.
A B bar. If you look at that expression, it can be reduced using Boolean algebra. What do you expect to have?
A, B bar.
No. Can you see B bar is common? So in brackets, what do you have?
bar plus or A.
A bar or A. But what's A bar or A?
1.
It's 1. So therefore our
It's
output is
B bar.
B bar.
B bar. Please note I've designed for you the counter, and DA is AX or B, then DB is B bar. Those are the expressions, but I want to do it for you in circuit maker because that's where we can be able to draw the diagrams very easily. I want you to get this very clearly. You can even just put them down. DA is equals to AX or B, and DB is equals to B bar. Put them down so that when I'm drawing the diagram, you can actually be able to check what happens. Or maybe I can even draw it here. First of all, before we go to the actual representation. So this is what you're going to have. I have my two D flip-flops, and they're just squares like that, rectangles. Just note that this will be your QA and this is your QB. So we usually call this A. This A bar, and this we call it B. And this will be B bar. So the clock is here, and the clock is here for this one. And then this is your DA. This is your DB. So we have an input here, and we have an input here. What happens? We have A XOR B. So you do an XOR gate here. And remember, that's how we do an XOR. And then you have your two inputs here, A, B. Where are they coming from? Please know that it will come from here. That's one of them. And B comes from here. I can also pass it here. And it goes to the input, it passes through that. So I've done for DA. Now, remember this B bar. That's B bar. So we have been told that DB is equals to B bar. So you pick B bar from here, just take it and feed it back here. And you will have your diagram, but you need to clock it. So the clock will be here. That's our clock input. So you take it directly here, and you also pick the same one and connect it here. And we call this our clock. It's called CRK. That's our diagram. So I can move it down here so that you can be able to see it clearly. Please note that that's our diagram for this counter. But in actual sense, when you're designing it using circuit maker, because I need to go there very fast, this one I can do it myself. circuit maker. I will share the screen. So I'm sharing the screen for circuit maker, and there we have it. So I want to design it for you. Anybody who is with me can also do it. And I will have a digital basics. We go to flip-flops. I pick the D flip-flops, 2 of them. I place them, one of them there. I pick the other one. I place it there. So you're done with the flip-flops. The next device you need to pick is
So you pick the D flip-flop.
Yeah, just pick the D flip-flops. D.
Okay.
These ones. Pick the first one. You can see all of them are there. They are SR, JK, they are there. I think the T is the one which is missing. So the next device you pick is the instrument, and the instrument you pick the pulsar. The pulsar is basically our clock. You can place it here. Then after you pick your pulsar, which is your clock, you can go down to displays. You also pick digital, you pick the hexadecimal display, and you place it there. After which we pick the gate. Which gate are we interested in? The 2 input XOR gates. Remember, we have an XOR gate to the input of DA. I think all those are the devices we require. So the next step is to do a wire tool and interconnect them. So we are being told that QA, that's A goes here, and I have it going there, and then QB goes there. Those are the 2 inputs which are going to the XOR gate. Then you can pick this one to go to DA. Those wires are overlapping, so maybe I'm not sure if it can move to the other side. Yes, it can. Then, still with the wire tool, connect QB to this one. And then clock pick the Q1. So Q1 connect it here, and connect it also up here, because you're being told that you need to use the same clock. And I think a diagram similar to the one which I done just before is there. So the next step is to now connect the outputs. This is QA, which is the most significant, connect it to 2. And QB is this one, which is the less significant, connect it to 1. After you're done with that, you need to do the simulation. So you go to digital mode, then run the simulation. Our speed is very high, so you can change it to 3. Just remove the 0, direct it to the 3. And you can see our counter doing the counting. 0, 1, 2, 3. 0, 1, 2, 3. 0, 1, 2, 3. That's our counter based on circuit maker. So please note that you can use circuit maker to do a counter just like that. But one can also use Tinkercad. And because I've already done it, I think I've done the Tinkercad one.
Excuse me. Mine is given only 0 and 3.
Eh?
Mine is given only 0 and 3.
You're saying?
Mine is given only 0 and 3.
Yes, it's counting only 0 and 3.
Yes.
Please check my connection. Can you even take an image of the same? I can even zoom it.
Okay.
Make sure your connections are like the way they are. Just take an image of the same. That's when I zoom it. In Tinkercad, I'm not going to show you how to do it. I've already done it, so I'll just run it. Though the one in Tinkercad I've done a 4-bit one, it's not a 2-bit, but I think you'll just be able to see the counting process. So I'm sharing that screen now. So this one I've done, the one which you can count up to 15. And I will start the counting. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Please note that the code is given here, though it has some complexity in terms of module, but I want to take a very simple one. Let me just do a counter for the one that you have just designed, you see how it appears in terms of the program, so that you realize it's very easy. Now I just want to show you the counter for. I'm just showing the counter for 2-bit. Are you seeing the code from here?
Yes.
I believe it's shared. So you can see low means 0 0, low high means 0 1, high low means 1 0, high high means 1 1. That's what we put here, and C and D will be affected. So if I start running that, you'll see only counting 0 to 3. And you compare the two. This is in software. So it's actually A, B which are being affected. So 0, 1, 2, 3. 0, 1, 2, 3. So we assume these ones are not there, these two. And that's your counter based on the 2-bit. You can actually take the code, it's here. You can also take the image. But this one, we just put it in 12 and 13, that's all. And then you connect your LEDs to power accordingly. That we have done before. It's just LEDs, nothing else, plus the resistors. Though sometimes you don't connect through the resistors.
And
do your program.
Resistors that you've used, what are the values?
This is 220 ohms.
The values of the resistors.
220 ohms.